In this chapter, we're going to look at carboxylic acids and nitriles. So a carboxylic acid has the general formula R bond C, double bond O, bond OH, like so. So this C double bond OH makes a carboxylic acid. And a carboxylic acid is going to have an acidic proton. And the acidic proton is that one right there. In the case of a nitrile, we have R bond C triple bond N, and this is a nitrile. So these are the two functional groups we're going to talk about the most. And as we have done in previous chapters, the very first thing we're going to start with is naming these things. So for carboxylic acids, there are both common names and there are IUPAC names. So let's look at some common names. If this R is an H, so we have H bond C double bond O bond OH, this is called formic acid. So no other carbon other than the one carbon is formic acid. If we have a methyl group there, CH3, C double bond O bond OH, this one is called acetic acid, which you may have heard of in general chemistry. We use this in our general chemistry labs. Furthermore, this is the stuff in vinegar. So vinegar is a 3 to 6-ish% acetic acid solution. So this is that acid. And another one is C double bond O bond OH. So we have a benzene ring with a carboxylic acid. This one is benzoic acid. And if we deprotonate this by adding a base and make this the sodium salt of benzoic acid, sodium benzoate, that is a common thing that is put in sugary drinks like soda to help prevent mold from growing in there. We can also have IUPAC names for these different things. So let's look at an example. I'm just going to do one example because we've done so much naming, but let's just look at one example. If we have a CH3, bond C, bond CH3, bond H, bond CH2, CH2, C double bond O, bond OH. So here we want the longest carbon chain containing the carboxylic acid. So we have 1, 2, 3, 4, 5 carbons. The base name of this is pentanoic acid. So if it was just a 5-carbon chain, we'd call it pentane, but because it's a carboxylic acid, we call it pentanoic acid. And this is carbon 1, 2, 3, 4. This is a 4-methyl pentanoic acid. So we would add oic acid to the name of the longest chain, and we use the usual names for those. So that is basically the names of carboxylic acids. Let's look at nitriles. So remember, a nitrile is R bond C triple bond N with a lone pair. This is called a nitrile. So let's look at an example. We could have some common names like one carbon bonded to this. Okay. This is called acetonitrile. Whoops. All right, just like acetic acid with the carboxylic acid, this is acetonitrile. We could have a benzene ring. All right. Whoops, I was drawing benzoic acid. Let me try that again. So we can have a benzene ring attached to a nitrile group. This is called benzonitrile. Instead of benzoic acid, it's benzonitrile. And like the carboxylic acids, we could have molecules that are essentially using the usual naming schemes. So let's take something like this. We have CH3, CH2, CH2, CH, CH3, and off of the CH we have a C triple bond N. So we again would want to identify the longest chain containing the nitrile group, which is this one. So we have 1, 2, 3, 4, 5 carbons. So we would call the base name of this pentan nitrile. So it's actually pentane nitrile. And then off carbon 1, 2, we have a methyl group. So this is 2-methyl pentane nitrile. So the end in the word nitrile. Since we've done so much naming and we went through this relatively quickly, let's take a look at the next section past the naming as well. So one interesting thing about carboxylic acids is they can have unusually high boiling points. So if we look at this example, CH3, C double bond O bond OH. This is acetic acid. And the boiling point of this is 117.9 degrees C. To compare this to ethanol, CH3, CH2, OH. It's a similar size molecule, still 2 carbons. It's still capable of hydrogen bonding with itself and having strong intermolecular forces. Here, the boiling point is only 78.3 degrees Celsius. So the boiling points are quite a bit different. And the reason for this is that this molecule is actually capable of dimerizing. So what you end up with is a CH3, C double bond O bond OH interacting with another acetic acid like so. And this dimerization can cause a massive change in the boiling point. So you can see here, it's almost 40 degrees higher for this one than this one. And this dimerization is what is responsible for that. When it comes to the solubility of carboxylic acids, generally carboxylic acids with 6 or more carbons are only slightly soluble in water. All right. So if you have carboxylic acids with lots of carbons, they tend to be not very soluble in water. So an example of that is if we have something, I'm just going to make this up, 1, 2, 3, 4. Okay, a 14 carbon carboxylic acid. This is not going to be very soluble in water. And in fact, this is called a fatty acid. All right, fatty due to this large non-polar section. And here we have this polar section. So this would only be slightly soluble in water. If we took the example of acetic acid with only 2 carbons, this is fully miscible with water. You can mix it in any proportion. So these have very different solubilities in water based on the number of carbons that they have. That being said, we can change the solubility by adding a base. So if we add, for example, NaOH to a molecule like this, I think I have the same number of carbons, this will deprotonate and we get Na plus and H2O liquid. So in this case, this molecule is soluble in water. Why? Because now it's ionic. And in fact, if you take a fatty acid and you add a strong base, what you make is soap. All right. Now, this may not be, sodium stearate exactly, because I didn't draw the exact right number of carbons, but these are fatty acids and can be used as soap. We're not going to talk about that too much in this course. Let's take another example. If we take benzoic acid, and if you've had general chemistry or organic chemistry 1 lab, you've probably done this. If you take benzoic acid and you add NaOH, or in the case of general chemistry, organic 1, we usually add something like sodium carbonate, just a different base, and we deprotonate this, we can make sodium benzoate, which if you remember before was the stuff I said is found in soft drinks and things like that to help prevent bacteria from growing. This will actually be found in the aqueous layer. So this is soluble in organic solvent because it's nonpolar. This is soluble in aqueous solvent, and you can use this for liquid-liquid extraction as we talk about in the lab. Take-home message for this class. If carboxylic acids have 6 or more carbons, they're only slightly soluble in water. If you're a biology student, knowing what a fatty acid is a good idea as well. All right, and I should mention, you can have unsaturated fatty acids, right, and polyunsaturated fatty acids, and all that means is that there's one, or in the case of poly, more double bonds. So that is basically just a little bit about the physical properties. Now, what I'd like to look at is the relative strength of these acids. And what I want to remind us all is that the lower the pKa, the stronger the acid. And I derived this for you already earlier in the course. So I'm not going to bother to derive it for you again, but generally speaking, the lower the pKa, the stronger the acid. I mean, it's just a rule of chemistry. I am not going to there's no math on the exam where you actually have to calculate pKa's, but you do need to know that if it says, this one has a pKa of 2 and this one has a pKa of 10, you need to know that the one with the pKa is a stronger acid. Or if it asks you which of the one following has the highest or the lowest pKa, you need to know whether it's asking you for the strongest acid or the weakest acid. So let's look at some examples here. Let's look at an alcohol. We already talked about this in the alcohol chapter, which is actually where I talked more extensively about the pKa, if you want to go back and watch that. So we have CH3, CH2, OH. If you recall, the pKa of this is 16. So this is not a very strong acid, but this proton is slightly acidic. We talked about at the time, if we have phenol, which is an OH directly bonded to the ring, because this would put a negative charge on oxygen if it loses a proton, and that negative charge could be stabilized by the ring and shared by the different protons. So if you have a negative here, this goes here, and then this comes in here, and then that can shift to here, and then the negative goes here, and so on and so forth. The pKa of this one is equal to about 9.9. Because the pKa of this phenol is so much lower than ethanol, we know that it's a much stronger acid. We can predict from the structure it'll be a much stronger acid because of that resonance stabilization that I was just talking about. Let's look at a carboxylic acid. CH3, C double bond O bond OH. Here, the pKa is equal to 4.76, which you may remember if you took general chemistry in our labs, because we actually use this one and we actually find the pKa of it in a titration experiment. So this is even stronger of an acid than either one of these two. And it's quite a bit stronger, right? About 5 orders of magnitude stronger than this one, which is quite a bit. Why? Because we have this acidic proton. Why is this proton particularly acidic? Well, it's because of resonance stabilization. When we lose that proton, all right, we get C double bond O, bond O. Now it has 3 lone pairs and a minus charge. Well, what can happen? This can go in here, and this can go up here. And what we end up with is a resonance form where we have CH3, C bond O. Now this one has the 3 lone pairs and the minus charge, and this one is double bonded, and now it only has the 2 lone pairs. So this is resonance stabilized. Sorry, this is a little off the screen. This is resonance stabilized, and you have the negative charge being stabilized on 2 very electronegative atoms, which is relatively stable. It's not super stable, right? It's still not a strong acid, but it's relatively stable, and that is why we have such a lower pKa. You remember that this one's resonance stabilized, but it's resonance stabilized with a negative charge on the carbon. Having the negative charge on the carbon is certainly better than nothing, right? But it is not as good as having those negative charges on the oxygen, and therefore we get the stronger acid. Now, if we look at an example of how we can look at pKa's, what can we do if we have different groups attached to these carboxylic acids? So let's take an example here. Actually, we're going to take a couple of different examples, but we're going to use as our base molecule CHHH, C double bond O, bond OH. So this is just a different way of drawing acetic acid. So instead of writing this as CH3, I just drew out the 3 CH3s. And here, the pKa is equal to 4.76, as we discussed a few minutes ago. Now, let's see if we put an electron withdrawing group on there. So let's take something like this, C bond OH, bond H, bond H, bond C double bond O, bond OH. I believe this is called glycolic acid. What do you think happens to the pKa? Does it go up or does it go down? Said another way, if it goes up, is it a weaker acid? Or does it go down, it's a stronger acid? Well, let's think about this. What are we trying to resonance stabilize here? Well, as we showed in the previous slide, what we're trying to resonance stabilize is a negative charge, right? And we were stabilizing that on the oxygens. So we're trying to stabilize an excess of electron density. A negative charge is an excess of electron density. So do we want an electron withdrawing group to help stabilize that, or is an electron withdrawing group going to destabilize that? An electron withdrawing group was going to stabilize that because it can pull away some of this excess electron density, and the pKa of this one is equal to 3.83. Said another way, this is a stronger acid. All right, lower pKa, stronger acid, that's the same thing. So this one is a stronger acid than this one. Now let's look at a more extreme example. What if we take C and we put 3 fluorine groups on here? Okay, and we have this attached to a C double bond O, bond OH. We now have 3 super electronegative electron withdrawing fluorine groups on here. And believe it or not, this is so much of a stronger acid that it's almost a strong acid. The pKa is negative 0.23. So this is a much stronger acid. To give you a perspective, HCl has a pKa of about -7. So it's not as strong as HCl, but for an organic acid, this is pretty darn strong. And the reason that it's so strong is because we have these electron withdrawing fluorines stabilizing, pulling that electron density, making that negative charge more stable. You have excess electron density here. This helps pull it away from that one spot and stabilizes the charge. The last thing I want to look at by way of this is, well, I guess it's not the last thing, but the next thing I want to look at is how this is affected by distance. So I'm not going to draw all the H's for clarity, but where I have a 3-carbon chain bonded to a carboxylic acid. I have a butanoic acid, if you will. I need to keep remembering to lift this up. So I have a butanoic acid. Again, this would be CH3, CH2, CH2. I'm not going to show them for clarity. In this case, we have the Cl here, and I'm telling you that the pKa is equal to 2.86. Now let's draw the same thing. All right. Same butanoic acid. Again, the hydrogens are not shown for clarity. And I'm going to put the Cl here. So the Cl is an electron withdrawing group, which makes this into a relatively strong acid, all right, relative to acetic acid. What happens if we put the Cl one further away? Does the acid become stronger or weaker? Well, by putting the electron withdrawing group further away from where the excess of electrons will be, it becomes a weaker acid, and this one, the pKa, is 4.05. Let's look at one more example. Not surprisingly, it's going to be on that last carbon. So let's have the C bond C bond C, bond C double bond OH. And this time we put the Cl right here. All right. When we do this, the pKa is equal to 4.52. So as the Cl gets further and further away from the carboxylic acid group, where the negative charge will be, the acid gets progressively weaker and weaker and weaker. The pKa goes up and up and up. Now, as a point of comparison, let's look at this one where we don't have any Cl at all. And if we look at this, the pKa is equal to 4.86. So it's still very slightly a weaker acid than this one, which makes sense because this at least has some electron withdrawing ability, but not much, right? These are pretty close. But then as it gets closer and closer, the acid becomes stronger and stronger. We can look at this in terms of groups on benzene rings if we're looking at benzoic acid. Let's look at the base molecule first here instead of looking at it last like we did in the previous case. Let's look at benzoic acid itself. So benzoic acid is slightly stronger than acetic acid because we can stabilize that negative charge through the ring. But it's not great, right? And it's not great because we have to put the minus charges on carbons. So there is resonance, but it's not great resonance. And here the pKa is equal to 4.19, which is slightly stronger of an acid than acetic acid. Let's look at what happens if we put two different groups. And one group is an activating group. So we have, that was a bad benzene ring, so let me try again. All right, we have a C double bond O bond OH, and we're going to put a methoxy, OCH3. This is an activating group. This is an ortho pair director when we talked about benzene chemistry before, or aromatic ring chemistry before. Let's look at the other example where we have a nitro group attached. And a nitro group is an electron withdrawing group, and this electron withdrawing group is a meta director and a deactivator. So what we want to compare is the acidity of this one and the acidity of this one to each other and to the base molecule benzoic acid. Remember that in all these cases, the acidic proton is the one on the ring, or excuse me, is the one on the carboxylic acid group. So when this leaves, we get a minus charge here. This group is an electron donator. If we donate electron density to the ring, we now have more electron density in the ring. We have more electron density over here. That's not good. We don't want an electron donating group. That's not going to help us stabilize a negative charge. In fact, it's actually going to make it potentially a little bit worse. And if we look at this, the pKa is equal to 4.46. You know, these are relatively close, but this is a slightly weaker acid than this one. How about this one? Well, in this case, we have an electron withdrawing group which can help to stabilize that negative charge and draw electron density away from the ring. And if we look to this, we find that the pKa of this one is a little bit lower. It's a slightly stronger acid, and it's 3.41. I don't know why I put a dot after it, but it's 3.41. So electron withdrawing groups and deactivating groups make the acid stronger. Electron donating groups and activating groups make the acid weaker. So generally speaking, what we can say is that activating groups make benzoic acid weaker, and deactivating groups, electron withdrawing groups, that's why they're deactivating, make benzoic acid stronger. All right, so that is all of the different groups that we need to look at in terms of relative acid strength for carboxylic acids. So before we finish up this section, I just want to make up a quick example, and we will go over that example just to see the type of question you might see on an exam. All right, so I have two examples here. So it says, identify the strongest acid. In the first case, we have an acetic acid with 1 fluorine. In the middle, an acetic acid with 2 fluorines on the adjacent carbon. And at the end, an acetic acid with 3 fluorines on the carbon. Which of these will be the strongest acid? Well, having 3 electron withdrawing groups is better than having 2, is better than having 1. But all of these would be stronger acids than acetic acid itself, where all of these are H's. So it's a CH3 instead of a CfH2, a CF2H, or a CF3. Okay, so this is our strongest acid. How about the next case? We have a benzoic acid with a methyl group. We have just benzoic acid, and we have a benzoic acid with an aldehyde group. So how do we get the strongest acid? Well, the electron withdrawing group, or the deactivating group, is going to be the group that gives us the strongest acid because it can help pull electron density away. Remember that when this loses a proton, we have a minus charge. That excess electron density can then be drawn into the ring better if we have a deactivating electron withdrawing group. Well, if you remember, methyl is slightly activating. This is the base molecule, so not activating nor deactivating. And here we have an electron withdrawing deactivating group because we can write a resonance form where there's a minus charge on O and a plus charge on C. So this deactivating group gives us the strongest acid.